You're standing in your laboratory, staring at an impossible sight. The machine before you hums with energy, its sleek metallic surface reflecting the blinking lights of instruments you've spent decades perfecting. This is it, the world's first functioning time machine. Your finger hovers over the activation switch, but doubt creeps in. Where will you go? When will you go? And perhaps most importantly, will you ever make it back? Time travel has captivated human imagination for centuries, from H.G. Wells' The Time Machine to modern blockbusters like Back to the Future. But beyond the realm of fiction lies a startling truth. The laws of physics don't just permit time travel, they practically insist upon it. Every moment of your life, you're traveling through time at exactly 1 second per second. But what if you could change that rate? What if you could slow it down, speed it up, or even reverse it entirely? The answer begins with a revolutionary insight from a young patent clerk in Switzerland who would forever change our understanding of reality itself. Albert Einstein's patent office in Bern was a modest place, filled with the mundane paperwork of inventors seeking protection for their ideas. But in 1905, while evaluating applications for electromagnetic devices, Einstein was wrestling with a problem that had puzzled physicists for decades. Light seemed to behave in ways that defied conventional wisdom about space and time. The prevailing view, established by Isaac Newton, treated time as an absolute constant. Time flowed like a cosmic river at the same rate everywhere in the universe. Everyone's clocks should tick in perfect synchrony, marking out universal moments that all observers could agree upon. Space, too, was absolute, a fixed stage upon which the drama of physics played out. But Maxwell's equations describing electromagnetic radiation suggested something troubling. They predicted that light travels at a constant speed regardless of the motion of its source or observer. This seemed impossible under Newtonian physics. If you're driving toward an oncoming car, the relative speed of approach should be the sum of both vehicle speeds. Yet light appeared to violate this common-sense rule. Einstein's breakthrough was to take Maxwell's equations seriously. If light always travels at the same speed relative to any observer, then our assumptions about space and time must be wrong. In a series of thought experiments, Einstein imagined what it would be like to race alongside a beam of light, to chase it at nearly its own speed, or to observe it from different reference frames moving at various velocities. The conclusions were revolutionary. Time, Einstein discovered, is relative. It bends, stretches, and warps depending on how fast you move and how deep you venture into gravity's embrace. There is no universal now, no cosmic clock keeping time for the entire universe. Your time is yours alone, and it can differ dramatically from someone else's. Consider this scenario. You're watching a friend rocket away from Earth at tremendous speed. From your perspective, their clocks run slow, their movements appear sluggish, and their aging process crawls to a near halt. But here's the truly mind-bending part. From their perspective, it's your clocks that are running slow. Both of you are equally correct. Time really is relative. This isn't just theoretical speculation. In 1971, physicists Haffel and Keating loaded precise atomic clocks onto commercial airliners and flew them around the world. When they compared these flying clocks to identical ones left on the ground, they found exactly the discrepancies Einstein had predicted. The flying clocks had gained time relative to their earthbound counterparts, proving that motion through space affects the flow of time. Today, GPS satellites orbiting Earth experience time at a different rate than we do on the surface. They're moving fast and sitting higher in Earth's gravitational field, both of which affect the flow of time. Without accounting for these relativistic effects, GPS would be useless. Your location would be off by miles within hours. Every time you navigate with your smartphone, you're relying on our understanding of time's malleable nature. But GPS satellites represent just the tip of the iceberg. Deep space holds far more extreme examples of temporal manipulation, cosmic laboratories where time behaves in ways that would seem utterly alien to our everyday experience. The desert stretches endlessly under a blazing sun, its silence broken only by the whisper of wind across sand dunes. Hidden beneath this desolate landscape lies one of the most sophisticated scientific instruments ever built, the Laser Interferometer Gravitational Wave Observatory, or LIGO. Here, scientists hunt for ripples in space-time itself, gravitational waves created by some of the most violent events in the universe. When two black holes spiral into each other billions of light years away, they create a cosmic maelstrom that literally shakes the fabric of reality. These objects are so dense that a teaspoon of black hole material would weigh as much as Mount Everest. As they orbit each other in their final death dance, they accelerate to significant fractions of the speed of light, warping space-time so severely that the resulting gravitational waves can be detected across cosmic distances. These gravitational waves travel across the universe at the speed of light, carrying with them information about events so energetic they dwarf anything humans have ever witnessed. The energy released in a typical black hole merger exceeds the combined light output of all stars in the observable universe, albeit for just a fraction of a second. LIGO detected its first gravitational wave on September 14, 2015, opening an entirely new window onto the cosmos. The signal, designated GW150914, came from two black holes roughly 30 times the mass of our Sun, colliding about 1.3 billion years ago. By the time their final gravitational cry reached Earth, humans had evolved from simple primates to a species capable of detecting these cosmic whispers. But these cosmic catastrophes also represent something else: natural time machines of unimaginable power. Imagine you could somehow survive near a black hole, that mysterious cosmic beast where gravity becomes so strong that not even light can escape. The event horizon, the point of no return, represents a boundary in space-time beyond which nothing can escape. But approaching this boundary reveals time's most dramatic transformations. The closer you venture to a black hole's event horizon, the more dramatically time slows down relative to the outside universe. This isn't science fiction. It's a direct consequence of Einstein's general relativity. Gravity warps space-time, and the more intense the gravity, the more severe the warping becomes. What feels like minutes to you near the black hole could represent years, decades, or even centuries to observers far away. From your perspective, time flows normally. Your watch ticks at its usual rate. Your heart beats normally, and your thoughts proceed at their customary pace. But to distant observers, you appear to slow down dramatically as you approach the event horizon, your image redshifting and fading until you seem frozen at the boundary of the black hole. This effect, known as gravitational time dilation, has been measured in Earth-based experiments. Atomic clocks placed at different altitudes tick at measurably different rates. The difference is tiny, about 22 nanoseconds per year for every meter of altitude. But it's real and measurable with modern precision instruments. In 2020, astronomers watched a star called S2 complete its closest approach to Sagittarius, a star, the supermassive black hole at the center of our galaxy. This star, with a mass about 14 times that of our Sun, follows an extremely elliptical orbit that brings it to within 120 astronomical units of the black hole, closer than Neptune is to our Sun. During this cosmic flyby, time dilation caused the star's clocks to run measurably slower than they would in normal space. For a human, the effect would be even more dramatic. Venture close enough to a stellar mass black hole, and you could witness the entire future history of the universe unfold in fast forward. Galaxies would collide and merge, stars would be born and die, and civilizations might rise and fall while you experience only moments. The cosmic microwave background radiation left over from the Big Bang would blue shift and brighten until the universe itself becomes a furnace of high-energy photons. But black holes aren't the only cosmic time machines nature provides. There's another phenomenon, equally strange and far more accessible, that demonstrates time's malleable nature every day above our heads. High in Earth's atmosphere, invisible violence unfolds continuously. Cosmic rays, particles accelerated to incredible speeds by distant stellar explosions, rotating neutron stars, and active galactic nuclei, bombard our planet's protective magnetic field and atmosphere. These cosmic bullets carry energies that dwarf anything we can produce in our most powerful particle accelerators, the most energetic cosmic ray ever detected, dubbed the Oh My God particle, struck Earth's atmosphere in 1991 with an energy of about 3 times 10 to the 20 electron volts. To put this in perspective, this single subatomic particle carried roughly the same kinetic energy as a baseball, thrown at 60 miles per hour. That's an almost incomprehensible concentration of energy in a single proton. When these cosmic rays strike air molecules, they create showers of secondary particles, including unstable particles called muons. These ephemeral entities are essentially heavy electrons, with 200 times the mass, but the same electric charge. They're created in abundance in cosmic ray collisions, but they're also inherently unstable. Muons live fast and die young. Their average lifespan is just 2.2 microseconds, barely long enough to travel 660 meters at the speed of light before they decay into an electron and 2 neutrinos. This presents a puzzle. Cosmic ray muons are created high in the atmosphere, typically 15 to 20 kilometers above Earth's surface. At the speed of light, even the fastest muons should only travel about 660 meters before decaying. How do so many of them manage to reach particle detectors on the ground? The answer lies in their incredible speed and Einstein's special relativity. High-energy cosmic ray muons move at 99.5% of the speed of light or faster. At these velocities, time dilation becomes significant. From our reference frame on Earth's surface, the muons' internal clocks run slowly, extending their lifespans enough for them to complete their atmospheric journey. From the muons' perspective, however, something different happens. Their clocks tick at the normal rate, but the distance to Earth's surface contracts dramatically due to length contraction, another consequence of special relativity. What appears to us as a 15-kilometer journey appears to the muons as perhaps only 1 kilometer, easily covered in their normal lifespan. This is time dilation in action, demonstrated millions of times every day in the natural laboratory above our heads. These cosmic messengers are unwitting time travelers, their high-speed journey through space translating into a journey through time. But it raises a tantalizing question. If muons can effectively travel to the future simply by moving fast, why can't we? The technical challenges are staggering, but the physics is clear. The energy required to accelerate even a small spacecraft to relativistic speeds is enormous. To reach 90% of the speed of light, you'd need to convert about 130% of your spacecraft's rest mass into pure energy, clearly impossible with conventional propulsion. Chemical rockets, which have carried humans to the moon, can barely reach 0.001% of the speed of light. Even theoretical propulsion systems like fusion rockets or antimatter drives would struggle to achieve significant fractions of light speed for crewed missions. A fusion rocket, burning hydrogen into helium with perfect efficiency, could theoretically reach about 12% of light speed. An antimatter rocket, the most efficient propulsion system physically possible, could reach much higher speeds but would require storing antimatter, one of the most difficult and dangerous substances to handle. But suppose we could overcome these engineering challenges, pack a spacecraft with enough fuel to accelerate to 99.999% of the speed of light, and time would crawl by so slowly that a round trip to Alpha Centauri, our nearest stellar neighbor, would take only about 2 years from your perspective. But when you returned to Earth, you'd find that over 9,000 years had passed. Civilizations would have risen and fallen. Technologies beyond imagination would have been developed, and humanity itself might be unrecognizable. This form of time travel, journeying to the future by moving fast, is theoretically straightforward. The universe has provided us with a roadmap, written in the behavior of cosmic rays and demonstrated by countless experiments. But what about the reverse journey? Can we travel backwards through time? The mathematics of Einstein's general relativity suggest that backwards time travel might be possible, but only under the most extreme circumstances. The key lies in manipulating the geometry of space-time itself, bending and twisting it into configurations that allow closed, time-like curves, paths through space-time that loop back to their own past. Picture space-time as a vast tapestry, woven from the threads of space and time. Massive objects like stars and planets create dips and curves in this cosmic fabric, much like a bowling ball would deform a stretched rubber sheet. These curves are what we experience as gravity. Objects simply follow the natural contours of curved space-time, like marbles rolling in the valleys created by heavier balls. But what if you could create curves so extreme that they actually fold space-time back on itself? What if you could weave a path through these folds that leads from tomorrow back to yesterday? In 1937, Dutch physicist Willem Jacob van Stockum published a solution to Einstein's field equations that described space-time around a massive, rotating cylinder. Van Stockum's solution contained closed, time-like curves, paths through space-time that would allow an observer to travel into their own past. It was the first mathematical proof that Einstein's equations permit, at least in principle, backwards time travel. But Van Stockum's cylinder would need to be infinitely long and rotate at tremendous speeds, making it physically unrealistic. Moreover, creating such an object would likely require exotic matter with properties that may not exist in nature. The quest for realistic time machines continued. In 1976, Frank Tipler refined Van Stockham's work, showing that a finite rotating cylinder could theoretically create closed time-like curves if it were dense enough and spinning fast enough. A Tipler cylinder would need to contain at least the mass of our Sun compressed into a cylinder just a few kilometers across, rotating billions of times per minute. Even if we could construct such an object, itself a task beyond current technology, the tidal forces near a Tipler cylinder would be lethal to any human traveler. The difference in gravitational acceleration between your head and feet would literally tear you apart long before you could complete a journey to the past. In 1988, theoretical physicist Kip Thorne explored a different approach. Working with his colleagues Michael Morris and Ulvi Yurtsever, Thorne investigated whether Einstein's equations permit the existence of traversable wormholes, cosmic shortcuts that could connect distant points in space and time. A wormhole, if it existed, would be like a tunnel bored through the fabric of space-time itself. Fall into one end near Earth, and you might emerge from the other end near a distant galaxy, having bypassed the normal journey through space. The concept wasn't new. Einstein and Nathan Rosen had explored similar ideas in 1935, but Thorne's team focused on whether such structures could remain stable and traversable. The Einstein-Rosen bridge, as the original concept was known, would naturally collapse too quickly for anything to pass through. But Thorne realized that with the right kind of exotic matter, a wormhole could be held open and made safe for travel. This exotic matter would need to have negative energy density, a property that violates what physicists call the null energy condition. But Thorne realized that wormholes could do more than just transport you across space. They could also transport you across time. The trick involves accelerating one end of the wormhole to tremendous speeds while leaving the other end stationary. Time dilation would cause time to pass more slowly for the moving end. After enough time has passed, the two ends of the wormhole would be separated not just by space, but by time itself. Step through the stationary end, and you'd emerge from the moving end in the past. The time difference between the two ends would depend on how fast and for how long you accelerated one end of the wormhole. In principle, you could create any amount of time separation you desired. But here's where the physics becomes truly exotic. To keep a wormhole open and steady, you'd need something that probably doesn't exist in nature: exotic matter with negative energy density. This hypothetical substance would push space-time apart rather than pulling it together, preventing the wormhole from collapsing under its own gravity. Quantum mechanics suggests that such exotic matter might be possible, at least in microscopic quantities. The vacuum of space isn't truly empty. It seethes with virtual particles that pop in and out of existence, sometimes creating regions of negative energy. The Casimir effect, first measured in 1948, demonstrates that quantum fluctuations can create measurable attractive forces between closely spaced conducting plates, effectively creating negative energy density in the space between them. But scaling this up to macroscopic sizes remains purely theoretical. The amount of negative energy required to stabilize a traversable wormhole would be enormous, potentially more than the total energy output of our Sun over its entire lifetime. Moreover, attempts to concentrate large amounts of negative energy might violate quantum inequalities that limit how much negative energy can be accumulated in a given region of space. Even if we could build traversable wormholes, they might come with built-in safety mechanisms that prevent paradoxes. Stephen Hawking proposed his chronology protection conjecture in 1992, suggesting that the laws of physics somehow conspire to prevent backwards time travel. Perhaps quantum effects would destroy any wormhole the moment it became a time machine. Perhaps the universe has an immune system designed to preserve causality. Hawking's conjecture is based on the observation that creating a time machine seems to lead to runaway quantum effects. As you approach the moment when closed, time-like curves first form, quantum fluctuations in the electromagnetic field become amplified. These fluctuations could become so intense that they destroy the time machine before it can operate, preventing any paradoxes from occurring. But not all physicists agree with Hawking's conjecture. Some argue that backwards time travel might be possible but self-consistent. You could visit the past, but you couldn't change it. Any actions you took would already be part of history, woven into the tapestry of events that led to your journey in the first place. This idea, known as the Novikov self-consistency principle, suggests that the universe would somehow conspire to prevent paradoxes. If you tried to kill your grandfather before he met your grandmother, something would always intervene to prevent you from succeeding. Perhaps your gun would jam, perhaps you'd miss your shot, or perhaps you'd discover that the man you thought was your grandfather wasn't actually related to you. The self-consistency principle leads to fascinating philosophical questions about free will and determinism. If the universe ensures that you can't change the past, do you really have free will when you travel backwards in time? Or are your actions predetermined by the need to maintain causal consistency? These questions become even more complex when we consider the many worlds interpretation of quantum mechanics. According to this theory, every quantum event creates multiple parallel universes, each representing a different possible outcome. Every time an electron chooses which slit to pass through in a double-slit experiment, the universe branches into separate realities where the electron made different choices. If the many worlds theory is correct, then backwards time travel might not create paradoxes at all. Travel back in time, and you might arrive in a parallel timeline rather than your own past. Kill your grandfather in this alternate timeline, and you'd simply prevent the birth of an alternate version of yourself, leaving your own timeline intact. This interpretation was explored in detail by David Deutsch in the 1990s. Deutsch argued that quantum mechanics not only permits time travel, but actually makes it consistent. In his view, a time traveler would interact with quantum superpositions of past events, and the universe would evolve into a self-consistent state that avoids paradoxes. More recently, physicists have proposed even more exotic solutions to the time travel paradox problem. In 2020, researchers at the University of Queensland demonstrated that it's theoretically possible to simulate closed time-like curves using quantum computers, allowing them to study the behavior of quantum information traveling backwards in time. Their simulations suggest that quantum effects might naturally prevent paradoxes without the need for external intervention. When quantum information travels backwards in time, it tends to evolve into states that are consistent with its own past, automatically avoiding contradictions. But even with these theoretical solutions, backwards time travel remains stubbornly speculative. The energy requirements are astronomical. The technology is beyond our current capabilities, and the fundamental physics remains uncertain. Most physicists believe that while backwards time travel might be theoretically possible in some exotic scenarios, practical time machines remain far beyond our reach. Forward time travel, by contrast, is not only possible, but inevitable. Every moment of your life, you're racing into the future at the rate of 1 second per second. Accelerate to high speeds or venture into strong gravitational fields, and you can change that rate dramatically. The implications are staggering. Imagine medical patients with terminal illnesses traveling to the future when cures might be available. A person diagnosed with Alzheimer's disease could potentially skip forward decades to a time when the condition can be reversed. Cancer patients could leap ahead to an era of perfect treatments with no side effects. Picture archaeologists journeying forward to see how their theories pan out. A paleontologist studying dinosaur extinction could travel to the future to learn whether their hypotheses about asteroid impacts or volcanic activity prove correct. Historians could witness how current events are interpreted by future scholars, potentially settling long-standing debates about causation and interpretation. Consider the possibility of escaping environmental catastrophes by leaping ahead to when solutions have been found. If climate change threatens coastal cities, their inhabitants could potentially journey to a future when sea level rise has been halted or reversed through advanced geoengineering techniques. But forward time travel also raises profound ethical questions. Who would have access to such technology? If time travel requires enormous amounts of energy and advanced technology, it would likely be available only to the wealthy and powerful. This could create a new form of inequality, where the rich can escape problems that the poor must endure. How would society function if some people could skip decades or centuries into the future? What happens to families when parents travel to the future but children remain behind? How do we maintain continuity in institutions, governments, and cultures if people can simply opt out of difficult periods? The legal system would face unprecedented challenges. How do you prosecute someone who commits a crime and then travels to the future to escape punishment? Can contracts be enforced when one party may leap decades ahead, potentially altering the terms or the context of the agreement? Even everyday concepts like age, education, and work experience become meaningless when time is no longer linear. But these questions, while daunting, are the price of understanding the universe on its deepest level. Time is not a fixed river, but a flexible medium shaped by speed and gravity, warped by massive objects, and potentially traversable through exotic geometries. Every particle, every beam of light, every moment of existence is part of this cosmic tapestry. And as humans, our curiosity compels us to explore its possibilities, whether through thought experiments, advanced physics, or future technology. How do contracts and property rights work when one party can disappear into the future for arbitrary lengths of time? What about marriages, employment agreements, and other social contracts that assume continuity of existence? These questions become even more complex when we consider that time travel might be a one-way journey. While moving into the future is relatively straightforward, returning to your own time would require the kind of backwards time travel that remains highly speculative. A time traveler to the future might be making an irreversible decision, cutting themselves off forever from their original time period. The psychological effects could be devastating. Imagine arriving in a future where everyone you knew is dead, where the culture is alien, and where your skills and knowledge are obsolete. Future shock, the disorientation caused by rapid technological change would be magnified beyond imagination for a time traveler. Perhaps the most sobering realization is that we're all time travelers already. Every second that passes carries us inexorably into the future. We can't slow down, speed up, or change direction. We're passengers on a cosmic express train, watching the landscape of time roll by outside our windows. But our understanding of time continues to evolve. Quantum mechanics hints at even stranger possibilities that challenge our basic assumptions about temporal ordering and causality. Quantum tunneling, for instance, allows particles to appear on the other side of energy barriers faster than light could travel the same distance through free space. Some interpretations suggest this might allow particles to effectively travel backwards in time, at least over very short distances. Quantum entanglement enables instantaneous correlations between particles across vast distances. When two particles are entangled, measuring one instantly affects the state of the other, regardless of the distance between them. This seems to violate the principle that information cannot travel faster than light, but the no communication theorem shows that you can't actually send usable information through quantum entanglement. Some theoretical frameworks suggest that time itself might be an emergent property, arising from more fundamental processes in ways we don't yet understand. Loop quantum gravity, one approach to unifying general relativity with quantum mechanics, suggests that space-time might have a discrete, granular structure at the smallest scales. In this view, time might not be continuous, but composed of indivisible moments, separated by gaps smaller than the Planck time, about 10 to the negative 44th seconds. String theory, another candidate for a theory of quantum gravity, requires additional spatial dimensions beyond the three we experience directly. These extra dimensions might be curled up and hidden from our perception, but they could potentially provide shortcuts through space-time similar to wormholes. Some string theory models permit closed time-like curves, though their practical implementation remains far beyond current technology. The holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary, hints at even more radical possibilities. If reality is fundamentally holographic, then our three-dimensional experience of space and one-dimensional experience of time might be projections of more fundamental processes occurring on a two-dimensional surface. Black hole physics continues to reveal new mysteries about the nature of time. The information paradox, the question of what happens to information that falls into a black hole, has led to proposals that space-time itself might be woven from quantum entanglement. If this is true, then manipulating entanglement might provide new ways to influence the structure of space-time and potentially create closed time-like curves. Hawking radiation, the theoretical prediction that black holes slowly evaporate by emitting particles, creates its own temporal puzzles. The radiation appears to be thermal and random, containing no information about the matter that fell into the black hole. But this seems to violate the principle that quantum mechanics is reversible and information is conserved. Recent work on the black hole information paradox has led to the firewall paradox, which suggests that the event horizon of a black hole might be surrounded by a wall of high-energy particles that would instantly incinerate any infalling observer. This contradicts the equivalence principle, which states that freely falling observers should not experience anything unusual when crossing the event horizon. These paradoxes have led to radical proposals about the nature of space-time itself. The ER equals EPR conjecture suggests that wormholes, Einstein-Rosen bridges, and quantum entanglement, Einstein-Podolsky-Rosen correlations, are actually the same phenomenon. If true, this could provide a new understanding of how information travels through space-time and potentially open new avenues for time travel research. The measurement problem in quantum mechanics also has implications for time travel. The many worlds interpretation suggests that every quantum measurement branches the universe into multiple timelines. But other interpretations, such as the de Broglie-Bohm theory or objective collapse theories, propose different mechanisms for how quantum superpositions resolve into definite outcomes. If consciousness plays a role in quantum measurement, as some interpretations suggest, then time travel might interact with consciousness in unexpected ways. A time traveler might carry their consciousness backwards through time while their physical body follows the normal flow of entropy and causation. Recent experiments in quantum mechanics have demonstrated increasingly exotic behaviors that challenge our understanding of time and causality. Quantum delayed choice experiments show that decisions made in the present can apparently influence the past behavior of particles. Quantum teleportation allows the complete information content of a particle to be transferred to a distant location, effectively creating a copy while destroying the original. The search for a theory of quantum gravity, a framework that unifies Einstein's relativity with quantum mechanics, might reveal new insights about the nature of time. Causal set theory proposes that space-time is composed of discrete events connected by causal relationships. In this view, time emerges from the partial ordering of these events, and closed time-like curves would correspond to cycles in the causal structure. Emergent gravity theories suggest that gravity and space-time might arise from more fundamental quantum phenomena, similar to how temperature emerges from molecular motion. If space-time is emergent, then its properties, including the direction and rate of time flow, might be alterable through manipulation of the underlying quantum substrate. Loop quantum cosmology, an application of loop quantum gravity to the early universe, suggests that the Big Bang might have been preceded by a contracting phase, with time flowing backwards before the bounce that created our expanding universe. This raises the possibility that our universe might be part of an eternal cycle, with time periodically reversing direction on cosmic scales. The anthropic principle, the idea that the universe must be compatible with the existence of conscious observers, adds another layer of complexity to time travel discussions. If backwards time travel were possible and commonly used, it might prevent the stable evolution of complexity necessary for consciousness to arise. This could explain why we don't observe time travelers from the future, even if such travel is theoretically possible. Advances in computational physics are allowing researchers to simulate increasingly complex scenarios involving time travel and causality violations. These simulations use techniques from quantum field theory, general relativity, and computer science to model how hypothetical time machines might behave and what effects they might have on their surroundings. Some researchers have proposed using quantum computers to simulate closed time-like curves, allowing them to study time travel effects without actually building time machines. These quantum simulations have revealed surprising results, suggesting that quantum effects might naturally resolve paradoxes that seem intractable in classical physics. The development of atomic clocks with unprecedented precision is enabling new tests of time dilation and other relativistic effects. Optical lattice clocks can now measure time with an accuracy of 1 part in 10 to the 18th power, allowing scientists to detect gravitational time dilation over height differences of just a few centimeters. These ultra-precise measurements might reveal new physics that could inform our understanding of time's fundamental nature. Gravitational wave astronomy, pioneered by LIGO and now expanded to include detectors around the world, is providing new insights into the behavior of space-time under extreme conditions. Future space-based gravitational wave detectors will be sensitive to even lower frequencies, potentially revealing exotic objects or events that could involve closed time-like curves or other temporal anomalies. The possibility of negative mass, matter that gravitationally repels rather than attracts, remains an active area of research. While no negative mass has ever been observed, some quantum field theories permit its existence under certain conditions. Negative mass could potentially be used to create stable wormholes or other exotic space-time configurations that might enable time travel. Metamaterials, artificially structured materials with properties not found in nature, have already demonstrated the ability to manipulate electromagnetic radiation in unprecedented ways, including creating invisibility cloaks and perfect lenses. Some researchers speculate that similar techniques might be applied to space-time itself, potentially creating temporal metamaterials that could influence the flow of time. The study of consciousness and its relationship to time adds yet another dimension to time travel research. If consciousness is fundamental to the universe, as some theories propose, then time travel might involve not just the transport of matter and energy, but also the navigation of different conscious experiences and memory states. Research into biological timekeeping, how organisms maintain circadian rhythms and age, might provide insights into the nature of time at biological scales. Some organisms, such as certain jellyfish, appear to be biologically immortal, potentially reversing their aging process indefinitely. Understanding these biological time machines might inform our thinking about temporal manipulation more generally. The intersection of time travel with information theory raises questions about the computational requirements for simulating or predicting closed time-like curves. If the universe is fundamentally computational, as some theories suggest, then time travel might be limited by the universe's information processing capacity. Standing again in that hypothetical laboratory, finger poised over the activation switch of your time machine, you might pause to consider these deeper implications. Time travel isn't just about the mechanics of moving through temporal dimensions. It's about confronting the fundamental nature of reality itself. The universe has revealed itself to be far stranger than our ancestors could have imagined. Time and space are woven together into a single fabric that can be stretched, compressed, and possibly even folded. The future and past might coexist in an eternal present. A block universe where all moments exist simultaneously. And, perhaps most remarkably, the simple act of moving fast enough or falling deep enough into a gravitational well can literally transport you into tomorrow. Whether we'll ever build practical time machines remains to be seen. The challenges are immense, the energy requirements are staggering, and the fundamental physics is still being explored. But one thing is certain: our journey through time will continue, one precious second at a time, carrying us forward into an uncertain but fascinating future. The greatest time machine ever built might not be a gleaming device in a laboratory, but the universe itself, a vast cosmic engine that transforms today into tomorrow, moment by moment, heartbeat by heartbeat, in an endless dance of space and time that we're only just beginning to understand. as we stand on the threshold of new discoveries in physics. From quantum gravity to consciousness studies, the mystery of time continues to deepen. Each answer reveals new questions. Each solution opens new puzzles. The quest to understand time's true nature, and perhaps to master it, remains one of the greatest challenges facing human science. Perhaps the most profound realization is that time travel is not just a scientific question, but a deeply human one. It touches on our deepest fears and desires, the fear of death and loss, and the desire to correct mistakes and relive precious moments. In seeking to conquer time, we're really seeking to conquer the fundamental limitations of human existence. But time, it seems, may always retain some of its mystery. Even if we develop the technology to travel through time, even if we solve all the paradoxes and overcome all the engineering challenges, we may find that the journey itself changes us in ways we never expected. The time traveler who returns from the future or emerges from the past may no longer be quite the same person who began the journey. In the end, perhaps that's the most important lesson time travel can teach us, that we are all temporary arrangements of matter and energy, brief patterns in the cosmic dance of space and time. Our consciousness, our memories, and our very sense of self exist only in the fleeting present moment, carried forward by the inexorable flow of entropy and causation. Every moment we experience is both an ending and a beginning, a death and a birth in the endless transformation of the universe. And in that shared journey, perhaps we can find meaning and purpose that transcends the limitations of any individual timeline or era. The machine before you hums with possibility, its circuits encoding humanity's greatest scientific achievements and deepest philosophical questions. Whatever future or past awaits beyond that threshold, the journey itself represents something profound, the endless human quest to understand our place in the vast, strange, beautiful universe we call home.